This video will provide an overview of how we calculate the gravity effects of geologic bodies and features. We'll begin by taking a look at some general geometric shapes, such as plane layers, intrusives, faults, and folds. Next, we'll examine the shape and amplitude of the gravity anomalies that we might calculate from these geologic features. From this basic understanding, we can extrapolate to more complex geologic settings. To do this, we often consider the gravity effects of an infinite slab, which we can use to model lava flows. A thin, two-dimensional prism is useful for modeling some special structures, such as horst blocks and grabens, anticlines, and stratigraphic features like channel sands. And finally, a thin disk can be used to model igneous intrusives, pinnacle reefs, and salt domes. For example, suppose we have a basement dome buried 5,000 feet below the surface. The dome has structural relief of 2,000 feet above the basement rock. We have a density contrast between the basement and sedimentary rocks of 0.2 grams per cubic centimeter. For this geologic feature, with this density contrast, we calculate this gravity profile. More sophisticated methods involve 2D and 3D computer modeling of gravity data. Let's consider this thrust fault that has carbonates with a density of 2.65 grams per cubic centimeter and clastics with a density of 2.40 grams per cubic centimeter. Using a 2D computer model, we calculate this gravity response. Notice the distinct gravity decrease at a horizontal distance of about 37,000 feet, which corresponds to the edge of the dense thrust sheet. Of course, we can also start with a gravity response and model a geologic feature to fit the response. Let's consider this gravity profile across a valley. As an initial model, we use this low-density body, the valley fill, which has a density contrast with the surrounding rock of negative 0.5 grams per cubic centimeter. This low-density body produces this gravity response, which has a reasonable fit to the actual gravity profile. Notice, however, the poor match between the two profiles in these areas. To rectify the anomaly, we modify the geometry of the base of the low-density body and calculate a new gravity profile. Now the calculated gravity fits the observed curve. In summary, this video has shown how contrasting rock densities for different geologic shapes and gravity anomalies can be modeled by computers to represent subsurface geologic structures.